Hello. So this is I'm going to go over some of the type stuff. So let's go with, okay, so the point of this recording is going to be to explain how type rules work, how to use them, and how this can be useful when you're writing your type checker. Okay. All right. So let's say we have some language. Let's try to make this a very simple language. We can do a number of things. Let's say that we can have pointers just to make it somewhat different from Patina, and also integers. So I can say, all right, the types that we're going to have are, we can have integers, right? And we can also have a pointer to an integer. Now, in Patina, I believe we also have, okay, that was wrong. In Patina, we also have bools and units. So you can have you could even, if we added bools to this, then you could have pointers to bools and so on, but let's not do that. So the other thing we're going to do for simplification here is to have only expressions. So we're not going to have statements or anything, no lists directly. All we're going to have is expressions, no functions. So when we define our expressions, we can say that those are one of some number of things. So you always need to have something that isn't recursive to begin with. So for that, we're going to allow constants. So we can have constants, which will have an integer, int. Notice that this is lowercase and that's uppercase. And then we need things to construct new integers. So we can say, for now, let's just add. We can add integers. We can add expressions, that is. And let's also add that we can have, we can dereference. So if you have a pointer to an int, then we can dereference it and we can get an int, right? So we can deref an expression. And let's say we can also use, well, this allows us to get rid of pointers. But let's say we want to make a pointer. Let's say that we can declare, we can use let. So we could say that we have a pointer to an already existing thing. But let's just say that we can create a null pointer. All right. So, or we can create a pointer to that eventually points to 0. So maybe we can say we can alloc a pointer, and this alloc is going to take a type because that tells us how many new spaces we need to allocate. And this thing will just return a pointer, something of this type. Or we give it a type and then it gives us a pointer to that type. And that'll be valid. So finally, we should have variables. So we can say that there's an ID, and that'll have a string attached to it. And we want to be able to create new variables. So we have let. So let's do let of. So let has a string and also because if we say let x equals E1 in E2, then we need two expressions. So expression 1 and expression 2. we can just do this for now. I think in the section, I didn't get time to do anything more than just these. Maybe not even deref and alec. So let's just go with this for now. Okay, so we want to be able to make rules to type check programs that look like this. So for example, if we have, we want to be able to say that there's something wrong with add of, let's say add of alec, if we allocate an int, say, and then also const of 5, okay? We want to say that this is wrong, and we can't do that with our syntax. So here isn't a concrete syntax, it's just an AST, but we can imagine that the AST represents the syntax of the language we have here. So this is allowed according to these rules here. And we can't actually use rules that look like this to rule out this sort of thing, at least not very much, as long as we want to contain all the things that should be allowed. So for example, something we do want to be allowed is add of const 3 and add of 2, 4, right? 2, 4. So this thing should type check, and this thing should not type check. And this is what the point of type checking is. It's to be able to say that that we can allow the top one in our program, but not allow the second one in the program, but not the first one. So we use rules to say what the types of things are. And then if an expression is well typed, then we can say, if it has a type, then we can say that, okay, this expression is one that we want to allow. And then the other ones we can reject in compilation. Okay, so we need rules for this. So some of you might be familiar with this way of doing proofs, where we can say we make some assumptions on the left. So A1, we can say we have it by assumption. Same thing with A2. And then we have something we want to prove at the bottom. So what we want to show is down here. And the way that we prove things is by saying, okay, we know that we know A3 because of some theorem that we've already proved, T1. And so this is the standard way of doing proofs in like high school geometry and maybe some other places, but that's not how we want to do proofs in with types. So the way we're going to do that is using a different syntax, which I'll show. So what we do is we have horizontal lines, and the thing that is proven goes at the bottom. So let's say we want to prove that 5 is odd, okay, right? Then what we can prove from that, then we put the premises on the top. So let's say we can have the premises that 5 is equal to 4 plus 1, and also that 4 is even, and also that x even implies, give me a second. And also that x being even implies that x plus 1 is odd. All right, so we have these 3 things here, and then some of these might need to be proved. So we could prove this one with a similar thing using that 3 is odd, and that x being odd means x plus 1 is even. So we end up with this tree. So in this case, it's pretty easy, but you could imagine that this one has some stuff written above it, and this one has some stuff written over here, and then maybe we're proving this actually, and then those have, so we get a tree basically. And at the bottom is the thing that's being proven. All right, so this is the structure that we want to use for showing things about types. All right, so now we're going to make some rules here to be able to conclude down here that the bottom one is good and the top one is bad. And what we're going to be showing proofs of is proofs that some particular expression is of some particular type. So we write that some E1 is of type, and then we put a type here. So people do tall, but I don't really know how to draw that. So I'm just going to say T. So we have, this would be showing that, okay, we know that E1 is of type T. And of course, this is only true in some circumstances. So you could have the totally trivial and completely useless rule that E1 is of type T also means that E1 is of type T, because obviously things imply themselves. But generally you have something useful going on here. So first we want to show, okay, what's the most basic thing here and what's its type? And here I would say that the most basic thing is the constants. So we can say that if we have a const of some n, this is of type int. Notice the capital here with an I. I'm saying that's a type, and this is true. In which cases? This is true when n is actually an integer. So I can say above that our premise for this is that n is an integer, and because this is something simple, I'm not really defining this. I'm defining this sort of outside of the scope of the type rules. So we can look at const 5 and we can see, okay, we know that 5 is an integer, which means that in the type rules, we can then conclude that const of 5 is an int. So this is one type rule that we have. It's good to name the type rules so you can say to describe how you're proving things. So let's say that this is tconst. Okay, so that was nice, and this was relatively simple. The fact that we had an integer is slightly harder here. Okay, so that's our basic way of getting integers. What's our basic way of getting pointers? That's down here, that's alloc. So let's write a type for alloc too. So we say here, we name this rule talloc, and we say that alloc of some type is of what type? Here, well, if we alloc an int, then we want the result to be a pointer to an int. And if we alloc an int pointer, we want it to be a pointer to an int. So it depends on what type T is here. In this case, it's pretty simple. It's just always a pointer of T. And we probably don't need to say it, but we can also add as a requirement that, okay, we judge that T is a type. So we don't end up saying, oh, actually, alloc of strawberry is a pointer to strawberry, when strawberry isn't a type. So we can add that requirement, avoid some issues. Yeah, so we don't end up saying that, although it's kind of ruled out by the syntax. Anyways, it doesn't really matter because this will be true in all the cases where we need it to be true. All right, let's go for something, let's go for adding. So we're going to make a new rule, tadd. And we want to be able to say that add, I'm just going to use a plus sign here because that's a nicer syntax. So let's say we have that E1 plus E2 added to E2 is of some type. Well, what type does it have to be? is always going to be an int. So when you add two things, you're going to get an int. We're not allowing you to add pointers. Well, I guess in C, maybe that's technically possible, but we're not doing that. But again, this is going to depend on what E1 and E2 are. We want to rule out this thing down here. And what's the problem with this? Well, the problem is that one of the things that we're trying to add is not an integer. And you can't add things that aren't integers under our rules. So what we have to do is we have to say, okay, we want to make the judgment that E1 is an int. And we also want to say that E2 is an int. All right, great. So this is our tadd. Finally, let's do tderef. This should be pretty similar. So you might want to pause the video and see if you can come up with the rule on your own, because all the pieces are there. So the thing that we want to prove is that deref of E, we can say E1, even though there's only one expression here, that this thing is of type T under what circumstances? Well, if E1 is int, for example, then we should never get the deref of int, of something of type int is of type T, because we want to rule that out. But we need to have something up here, a premise here that's able to rule that out. So one of the things, since T has to be a pointer, let's say that T is of some type pointer, the E1 is of type, okay, let's erase that. We want to say that E1 is a pointer type. And in particular, it has to be some particular pointer type. So E1, when we dereference it, it should get something of type T, which means that it itself should be a pointer to a type T. Okay, I hope you, this shouldn't say tconst, it should say tderef. I don't know what I was doing there. So I hope you were able to come up with that rule yourself. But if not, we'll talk about what to do here. So Alec, let's try to do this bottom one here. We want to show that add of const 3 and add of const 2, const 4 is what that should say. I guess I just removed it for the sake of being short. Let's prove that this thing is of type int using these rules. So when you do this sort of proof, you always work backwards, top down instead of bottom up. So I'm going to erase this proof afterwards, so I'll just use all the space here. All right, so we have on the bottom, we're saying that const of 3 plus const 2 plus const 4 is of type int. And so what are the premises? Well, we can use tadd here to go backwards and see, well, we need E1 to be of type int, and we need E2 to be of type int. So let's say, so E1 here is const 3 and E2 is const 2 plus const 4. So then we just add those premises up here. So const 3 is of type int is one requirement. The other requirement is that const 2 plus const 4 is of type int. All right, so let's look at this one over here. Const 3 is of type int. Well, we don't have any adds here anymore. We can just go directly to tconst. And we can see, okay, the pattern applies, so we can just put it backwards and say, all right, 3 is an integer, which means that const 3 is of type int. And then this one needs to be proven. So here we can use tadd again, and we get const 2 is of type int, and also const 4 is of type int. And again, hopefully at this point you can finish this off yourself. So we can say const 2 is of type int. Why? Because 2 is an integer. And const 4 is of type int because 4 is an integer. So here, if you want to look at the proof from the bottom up, in this case, it's, I mean, the top is the bottom of the tree or something. So if you want to look at it starting from our premises, then you can look at it from the top of this proof downward. So we can see that, okay, 2 is an integer, 3 is an integer, 4 is an integer. So const 2 and const 4 are of type int, and const 3 also. And then const 2 plus const 4 is of type int. Therefore, when you add the two things, you get another int. Okay, so this is how you do the proof. You'll notice that we haven't covered ID or let yet. That's because they're somewhat more complicated. So in ID, if we have, say, the string, the program add of x const 5, this right here, it depends. So in some circumstances, this should be well typed. If we said let x equals const 5 in add x const 5, then that should be well typed. Then add of x const 5 should be of type int. But if we said, say, let y equals const 5 and add x const 5, then that shouldn't be well typed because x hasn't been defined yet. It has no type. So this is where we introduce an environment. So the environment that we use is gamma normally, I think. Let me erase this. So we're going to need a couple of things. I'll give the description of what the judgment is now. So first we have, okay, so our judgments down here were stuff like, okay, T is a type, or this expression is of type is of this type. But what we need to add is we need to add that there's in a particular environment, it's true. So we're going to have something that looks like this. Gamma entails that, say, let's change this one, for example. Under some particular environment, in fact, any particular environment, const n is going to be of type int. And so we don't need to, just to look at the pieces here, gamma is a variable. Gamma is a variable that refers to an environment. It stores all the information about the types of different variables. Then this turnstile thing, this is sort of like implication, not really. What it means is that in the environment, which is the thing on the left, the thing on the right is true. Or we can say the thing on the right. So what this means over here is that, give me a second, is that in any particular environment that we call gamma, it's true that const n, we can conclude that const of some integer is an int. So talloc, this is going to be pretty much the same thing, right? Under any environment, this is true, but tadd and tref are different. So in tadd, if we want to conclude that in some environment, E1 plus E2 is of type int, it's possible that E1 and E2 have variable names in them, such as this example down here. So what we need to do is we need to use the environment to judge each of the sub-expressions of it. So we can say, okay, this is true only when in that same environment, E1 is of type int, and also in that same environment, E2 is of type int. The same thing down here. All right, so now let's get to our ID. So in some environment, we want to be able to judge that ID of some string is of type T when? Well, we've said that the gamma here holds the information, and we can sort of treat that as a black box. So we can just say, all right, gamma tells us that X is of type T. And in that case, moving into the type rule system, we can conclude in that environment that ID of X is of that type. So we can call this TID. Now, the most complicated one here is let. So if we have a rule where we say, all right, we want to be able to conclude that let of some string X, some expression E1, and some expression E2. Maybe I should write this out in its more standard form. So we want to say that let X equals E1 in E2. This thing should have some particular type. Let's say, let's just call it T. In which circumstances? Well, if we say let X is equal to alloc of 4, alloc of int in const of 4, well, in this case, X isn't used at all. So the type that we use is E2s. So for now, this is actually wrong, but for now, let's say we want to be able to conclude that in the current environment, E2 is of type T. And well, X, when we say X is equal to E1, then what matters for type checking here is that E1's type is being attributed to X. So let's say that, let's just say, okay, in this environment, we have that E1 is of type T1. And this has to be the case because otherwise, if we let X equal something incoherent, then we want this program to break. So we have to say, okay, E1 is of some type. Then what we also need to say is that X is equal to something about X. So we want to use X, now that we've defined it, in this new expression over on the right, in here. And so the reason why this thing is wrong is that E2 needs to have this new information. So if we had, for example, let X is equal to const 4 in, let's even just say ID of X. Then this thing should type check. So we need to, but on its own, ID of X isn't going to type check. So we need to add the environment, add the new variable into the environment. So what we can do is, instead of using the current environment to check E2, we'll use an augmented environment. So we can say, all right, this, and we add in that X is of type E2, of type T1. Then it should be true in this new environment that E2 is of type T. Got it? Okay, so that's everything that we covered in section. I think I'm going to be done with that for now. Okay. There might be an additional thing going up in a bit, but yeah, this is the stuff covered in section. I hope it's also better for you this way than it is with the raw recording. Let me know. All right.